and then the smart board recording, and they'll have to wait for a longer period of time to see their exam one papers. In general, the exam went well. I think people did well. There are 8 students in the 90s and 5 students in the 80s or upper 70s. So if you had to assign grades, the A grades, B grades, maybe down to B minus. So everybody's in either very good shape or in a good shape for the class. So keep up with the homeworks. Figure out where you lost points, kind of what is the style of where points were taken off. And figure out where points were taken off. The second exam, along with the practice, will give you more, have a better idea of kind of the style of the questions, maybe how to prepare. It builds somewhat on the material that we do, but then there are some new topics. But there's plenty of points left to go in terms of the homework, the second exam, final, and project. But this is a solid performance. A lot of the descriptions of algorithms like Bootstrap and things were detailed. Often I found it like a small thing that a little detail could be added there to make it a little more specific. But generally I'm pleased. If you want to talk about your exam at any time, feel free to come by office hours, arrange a special time, and we can go over explaining what some of my marks would mean. Solutions are posted on the site here under assignments and down under exam 1. There's solutions posted. I didn't print them out, so you could look at those as well. And we'll talk about those. I'm also handing out a revised, just updated schedule, right? So I hadn't written out all the details toward the end, but this is pretty much how I think the semester will go. One thing on this is for next week, right? Monday, of course, is the college break, so I won't have classes or office hours, so that Monday, Tuesday. Wednesday we have class, and we'll continue looking at this topic of Fisher information, and it's one more thing that can be done with the likelihood function, right? And then Friday, there's also no class. I'm attending a VGN workshop at Vermont Genetics Network Research Workshop, and that day in the later afternoon is Pi Mu Epsilon, which is Math Honor Society seminar. And so some individuals will be inducted into that Math Honor Society, and there's also a speaker, and I think that would be an interesting one to do because it's kind of at the intersection of combinatorics and genetics and mathematical formulations, a little bit statistical, but in any case, that would be there. Now, homework 5 will be a couple problems on this Fisher information topic we'll talk about today and a little bit then. I will be coming back to campus, so I can't be here during our class, but the homework 5 could be submitted to my office. And so to keep this kind of going, being on this Friday schedule of having things due, there'll be just a couple of questions there. I'll be in my office on Thursdays. Office hours will be shifting. So instead of having a Tuesday office hours, I'll have a Thursday office hours. So Thursday will be an office hour, and then this thing will be due on Friday. So we'll have another lecture on this, and then an office hour, and then a couple of problems due later then. And my office is in Jean Marie, 259, just down one floor. And so I'll either put a folder out there, or you can slip it underneath the door, and I'll get them that way, and then so we can keep kind of moving along. So, but any questions about that? One thing about the Vermont Genetics Network is also provides funds for students to work on projects, and the math department, math and statistics, with some in chemistry and biology, has this STEM grant, which provides some financial aid to people doing either double majors or major minor combinations between quantitative field and life sciences. And this would be kind of a way to leverage, or you write in a grant, there's a certain synergy between getting funding on that and this other thing to bring more students into quantitative work in the life science. And hopefully that works out. So, but anyway, this is posted also on site, and so it kind of fleshes out a little bit more of the topics that we'll do for the course. For the close that, the exam. So this first one, let's just look through the problems and see what we can say. This one was, there's this density, we had 50 observations, and so you write the product of those densities, and this is how you combine them. And if you take the logs, you get this thing, and take the derivatives, you get these. And so the MLE was 3 over x bar. This is 1/2 kind of factors out to the front. So some people had an extra 2, like a 1/2 lambda or something like that that kind of crept in there. So some people had 6 over that, or they had a 2 in the denominator. So the treatment of that extra 2 just caused a little bit of confusion, but it worked out. Right? For giving the picture of the MLE, some people, if you got a number that was a little bit less, and you said it was over here, that was fine. One point is that the MLE is actually the value of lambda. So this is the height of the curve up here, and then it maps down. So some people did something like the derivative up there, or they didn't kind of say that it's actually that value. A few details there about the bootstrap. Some did kind of the first 3 steps really of describing the bootstrap, but kind of left off something that we would calculate as the standard deviation of all those. Most people did say something like that in words. This would be kind of a formula for that. But generally, they were quite good. It was quite organized in terms of the presentations that were there. This density, by the way, is a gamma random variable. It's one, with a parameter of, I think, 3 in lambda. So it was taking a specific instance of 1 and then making it big. In the experiment, the hypotheses generally were stated well. There, in terms of the test statistic, people got the numerical value. One thing that came up for some time is the symbols really about the parameters are usually distinct from the ones about the sample average. Right? Some people just use the same symbols for both, or put like an M of F, M of, right? But so trying to distinguish between the parameters and the sample is a theme that we'll have for statistical inference and estimation. Right? And in many applied problems, it's good to have the units if you can do that. So they didn't usually take off for that, but in the hypothesis testing, this was the distribution of the permutations. And one thing that happened a couple of times is that people said, no, it is not significant because our number's not in there, or something like that. Right? Well, the logic that actually happens is that this is the distribution of the average differences under the null that says they're equal. So if you're extreme under that, like ours clear out here, then we call that statistically significant. Right? It's statistically significant different than 0. Right? If it's 2.55 centimeters. If it was possibly 0 centimeters and not statistically different, then you would have a number. The observed average would have been something here. And so, but the language, so yes, the difference is statistically significant, meaning that the observed value is inconsistent with the 0 distribution or the null distribution. So just that actual use of terminology. Some people said, no, it's not significantly different, but we reject the null hypothesis. So the interpretation was that our sample was, so I didn't take off 100% of the points for that, but there was just that little inconsistency. But if the majority of the statement seemed to be expressing the fact that we don't believe 0, then I gave most of the credit there. This is this normal one. By the central limit theorem, x bar is approximately normal with this mean and standard deviation. And so if you calculate the difference from 32 down to 31.8, it's only 0.22. So that's not very big. So under a normal, well, the chance that you're bigger than that is less than 1/2, but it's still pretty common, right? If you're outside of 2 or -2, then that's pretty unusual. But being that close to 0 on the standardized scale is not so unusual. And this was the answer to this one, how could you use simulation, is actually, there's just a little bit of complication that I didn't really require everybody to see, right? So the central limit theorem in part A really works even if the data themselves are non-normal, right? So the distribution of x could be whatever it is, right? And so the average height of these spruce trees, well, maybe it's non-normal. Maybe some really get shaded out and end up really small, and then some others grow quite well, right? Maybe there's some dominant ones and so on. And so there's more of a mixture of healthy trees and diseased trees or something. So the x's might themselves be non-normal, but then x bar, the average of those things, of a bunch of them, tends to have a more average sampling distribution. So if you took many samples of 40, the distribution of that average could be normal. Right? So how would you simulate that? Well, if you had the x's, you could bootstrap it and use those values. If you knew what distribution it actually was, like if x was actually normal, you could sample from that. But if you don't have the x's and you don't actually know the distribution, then you can't really sample from it, which is really a complication. But if people assumed it's normal and they said they sampled from the normal with the mean of 3.18 and the standard deviation of 5.6, which would be the individual trees, that would work. Another way you could kind of just get at that probability of being greater than 0.22, you could just generate x bars from its sampling distribution with the smaller standard error. Right? That would probably be pretty accurate. So there's just a little subtlety there is what's the distribution of x and what's the distribution of x bar. And that's kind of the point of that. And the question didn't really hone in on that, and we didn't discuss a lot of examples like that. So I was pretty lenient in terms of how that answer was phrased, but technically there's a little complication that's in there. And then this one, these two distributions were quite similar, as it turned out. I think that the MLE one was a little shifted, so people compared the averages, the spread was kind of the same, shape was kind of the same. I think the MLE is a little bit more that way. So you could say things like that. Where did these things come from? Just in case you're curious. Initially I was trying to find one, and I thought, maybe you don't want to have to try to find that one on the exam. It looks a little funny, right? So if the xi's have a beta distribution with parameters 1 and 1 plus beta, the expectation of one of these is 1 over, and then you add the two components together, 2 plus beta. So method of moments says you equate 1 over 2 plus beta equal to x bar, and then you solve for beta. Taking 1 over both sides, here's 1 over x bar. So the method of moments estimator is it's 1 over x bar, minus 2. Right? That's what it ends up being in this case. That's where that came from. Now the maximum likelihood estimator, we need the density. So the density of the xi's for this beta happen to be 1 plus beta, 1 minus xi. Oops. Right. Raised to the just beta power. Now the beta is a distribution where the x's are between 0 and 1. So you can take 1 minus and you still have a positive value there. Right? So that's the density. So the density of all the observations is a product of this thing, 1 minus xi raised to the beta, which becomes 1 plus beta to the n, and then each of these 1 minus xi is raised to that same power, so you can multiply them all together and raise all of that to the power. And you get this likelihood function for beta. And then we take the log and differentiate that, taking the log likelihood of beta gives us n times log 1 plus beta. And then this thing can be written as beta times the sum of the logs of 1 minus xi. And we differentiate that thing, set it equal to 0. I'll write that on the next page for space. So we see things. So differentiate that log of beta with respect to beta. You get n over 1 plus beta, because it was log of 1 plus beta. And then there's just a sum of the logs of 1 minus xi. We set that being equal to 0. And then solve for beta. And you get the beta hat for the MLE, kind of jumping some steps. It's either n over the negative, the sum of the logs of 1 minus xi. There's two little parentheses in there. Minus 1, or as I wrote it in the exam, then it's n plus the sum of the logs. Common denominator, yeah. Log of 1 minus xi over the negative of that sum of logs of 1 minus xi. So when I first did this, I thought, boy, that looks kind of funny. Right? Because these things really come close. And so it's kind of surprising that they actually kind of have similar distributions. I don't know if there's another way to figure out why they're similar, but they just experimentally they seem to be. Right? And so even thinking about this, so xi, I like to think about, does this seem reasonable? Well, xi is between 0 and 1, so 1 minus xi also is between 0 and 1. And so then the log of that is between negative infinity, right, and 0, because the log of 1 is 0. And so the sum is all these negative things. We take the negative of it and it's positive. The beta parameter space is greater than 0. And so I think this works out as long as the sum up here is not too small, less than the sample size. So it's possible it could have some problems and you need to kind of bound it at 0, but I'm not sure. Right, so, exactly. Anyway, that's where that one came from. And so instead of giving you this one with all these negative logs and things like that, I thought I came up with one other one. But I thought it was an interesting example to see how two estimators can look so different. But their performance seems to be kind of similar. It's kind of amazing.
Thank you for sparing us.
I didn't think you needed to kind of a headache to deal with. Not too bad, but. But any questions on the exam? Anything in particular? So I tried to indicate, where points were taken off or make notes in there. But let me know if you have any questions. Look at the solutions. It's likely that some part of this will come back on the final, maybe the maximum likelihood, maybe Bootstrap will be used for other purposes, simulation for other purposes. And so it's worth reviewing, getting a good handle on this material, whether you do it right away or wait till later. The solutions will be there to look at. So the new topic is to say a little bit more about maximum likelihood estimation and what we get. Right. So the one result, right, is the maximum likelihood estimates are consistent for their parameters. That as the sample size gets large, the bias goes away and the variance gets small, and they become consistent. And so that's very nice about that. But we might have the further question, what is the sampling distribution of a maximum likelihood estimator? That is, if you could take more samples, right, what would the distribution appear to be, right, of cross-repeated samples? Right? That's the inference type of question that we're asking. This is sometimes called a frequentist approach. a repeated sampling approach, well, what would it be? Right? We have one way that we could simulate it. Right? We could do a bootstrap. Right? So bootstrap would give us one way to look at this. Right? One approach, bootstrap. And as you described on the exam, right, if you had a set of n observations, you could randomly resample from those with replacement n times, get a new bootstrap data set, calculate the MLE, do that process 10,000 times, and you'd have 10,000 maximum likelihood estimates, and you could look at the distribution. Right? So that would describe the sampling distribution, and we could do that. Right? But something else happens in large samples. I'll write it on the next page. With larger samples, there is a theorem 3.6, fifth theorem 6.3.6, right? So let x1, x2, ... be an independent sample from a density with a certain parameter. So f is some probability density function, or a function that gives you probabilities at certain points, right? And the theta is an unknown parameter that affects those probabilities or that densities. Let theta hat n be the maximum likelihood estimator of theta. So it's whatever formula or procedure that it's supposed to do. Right? There's to get a maximum likelihood estimate from writing out the joint density, taking the logs, derivatives, setting equals 0, solving. Right? We're going to assume that this density is smooth in theta and that n is large. Right? So smooth in theta comes operationally down to, can you differentiate with respect to theta? Right? Because if it's smooth function, you can take a derivative of it. Right? So most of our functions that we're taking derivatives of, they're not discontinuous at a point. It's not like you're going along and suddenly, boom, it's a different density at a different level. It's a continuous change. So we can differentiate. So this applies to almost everything we work with. N is large. It's kind of a relative thing, right? If the distribution starts out fairly normal, you don't need a very big n. But if it's really skewed, like log normal, you might need a few thousand or something. But usually the 40 to 140 or something like that is adequate. You could look at a bootstrap to see if the sampling distribution looks kind of normal, right? Then theta hat n is approximately distributed as a normal distribution centered at theta, and its variance is 1 over n times something called the information, called Fisher information. And so this is the result. We'll explore what this thing is, but this is the approximate sampling distribution of the MLE. And what this means that we can do is we can estimate the variance. We put a little hat on that, kind of estimated variance, by plugging in our value, our MLE of theta, into whatever that equation is. So this will give us our approximate variance. And then because of the normality, we can make a 95% confidence interval for theta. Right? And we don't have to do the bootstrap or do any other simulation. And so we can report then a 95% confidence interval for theta as theta hat in plus or minus 1.96, which is about the 95% cutoff value for the normal, times 1 over n times the information for theta, evaluated at the MLE, and the square root of all that thing. Right? So this gives us a lower point and an upper point, and so that becomes our 95% interval. Right? So the maximum likelihood estimation procedure gives us a way to get an estimator for a density function. But it's also going to give us a way to evaluate the variance and get a confidence interval. So it's kind of a package together. With the method of moments or some other things, you have to do some more probability theory to figure out the means and variances of your estimator, or do bootstrap, or it's a different approach. This one's kind of nice because it's all kind of fit in. And one thing that it does is it focuses on the likelihood, the statistical likelihood for the data or your probability model. There's something I find desirable about that, right? So let's look at this information criterion thing. This Fisher information, right? This I of information about theta, kind of the information measure that is in the content of one observation about data. How much information do you learn about a parameter from having one observation? And it's, if you take the log of the density at one observation and take the derivative of that thing with respect to theta, right? And then square it and take the expectation, the probability theory expectation of that, that's what it's defined as. Now, if f is a smooth function, this thing actually is equivalent to the negative of the expected value of the second derivative of the log of a single density. So what this says to do for all of our f's that are smooth, technically from the calculus perspective, there's something about differentiating under an integral sign, exchanging the order of integration and differentiation that's going on. So always a fun topic to explore at a later point, right? And so there's the density, the log of it. We take the derivative twice with respect to f. So this is the smoothness. You have to be able to take these derivatives. Then you do have to take this expectation. Sometimes the random variable goes away and it's just a simple formula. Other times it's as simple as using the expectation formulas from the back of the book to get that. This is going to be negative because these things are concave. Second derivatives are negative. So we take the negative of that, and then our variance of our MLE is 1 over n times that information. So as information gets bigger, our variance gets smaller, right? Which is kind of a nice interpretation. And if we have independent observations, we get n times the information. Right? So our information adds up, and our variance is 1 over that. Right? So we'll see how this works. Yeah, some examples, right? So where is that? Let's start with an example where the xi's are Poisson random variables. Right? The density for x given that lambda is lambda to the x e to negative lambda over x factorial. To find the MLE, we'd have n observations. And so the joint density of all of n of them, my little tilde means like the vector of all of them, is a product of I going from 1 to n of the lambda xi e to negative lambda over xi factorial. And so you put all that together, you get lambda to the sum of the xi, the e to the negative n lambda, and this thing with all the xi's down here. And you take a log of that. This is the likelihood of lambda. And the first two parts, the numerator parts, are relevant. There's the sum of xi times log lambda minus n lambda. There is this extra part from the denominator, but that's not going to have any lambdas in it. So when I differentiate it, it goes away. So let me just save space by doing that. If we differentiate that thing with respect to lambda, we get the sum of xi over lambda minus n, so that equal to 0. And that comes out to lambda hat is simply, x, or just x bar actually. So if you add this to this side and multiply, you get the sum of xi is n times lambda, and you divide by n, and you get this one. It was something like geometric, or negative binomial, exponential, some of those ended up with 1 over x bar. It looked quite similar, but maybe you'd have a lambda up top, and then it would end up being 1 over. But that's the MLE. What's its large sample variance? Well, x bar, is pretty simple. So probability theory does say the expectation of x bar is just going to be lambda, just its mean, and the variance of x bar is just going to be lambda over n. So using probability theory about the Poisson distribution and basic expectation and variance does get us that. Right? But we can go through this information theory, right, and see what we get. So we could do bootstrap, we could use some probability theory to get it part of this one because x bar is pretty direct. What does the information theory say? Information. So we start with one observation. As lambda to the x e to the negative lambda over x factorial. Now we take the log of that. For information, we're going to, and independent observations, we're just going to work with one density. Right? Before, to find the maximum, we need all n. Right? For this one, we're just going to work with 1. So the log of that has x times the log of lambda minus lambda minus the log of xi factorial, or x factorial. I don't need to consider. Right. And then we differentiate that twice. Right? So I'm just going to write d lambda of that thing. Kind of think about writing that. That's lambda minus 1. And then the derivative of that is 0. Right? And we differentiate it again. Right? D squared d lambda squared. So it would be negative x over lambda squared.
Will we ever be in a situation where we would have to know how to do log of a factorial?
The log of the factorial, well, not really.
Yeah, I know it's a random question, but I just realized.
Yeah, well, so the log of factorial, because this is it's x times x minus 1 times x minus 2.
Yeah.
So you could write that as the sum, I going from kind of 1 up to x of log of I, something like that. And so you can rewrite it to where you, instead of multiplying all those things together, are adding all the integers on the log scale. But we don't really need to do it.
I know it doesn't really matter with this problem.
Right. So this is close to what we got, right? I would take the expectation of that. Information is kind of an what's the average content of each one of those. Now the expectation of just one observation is lambda for a Poisson. That's the mean. Right? So if you look up the Poisson, the mean of it is lambda. So the expectation, I'll put the negative on there too, d squared, d lambda squared of that thing. Right? I'll write it here so it's written down at least once. Log of f of x given lambda comes down to, the negative gets rid of that negative. So we need the expectation of x over lambda squared, and that's just lambda over lambda squared, or 1 over lambda, right? That's the information content in one observation, right? From that distribution. Right? Each one gives you 1 over lambda piece of information. So if lambda is big, I guess you're getting less information. If lambda is small, you're getting more information because you're getting a small observations are only consistent with small lambdas. Big values can be consistent with the whole range of lambdas. So that's the kind of information from 1. Right? So the variance of our lambda hat in large samples is supposed to be 1 over n times the information about it. Right? So it's 1 over n, and this thing's 1 over lambda. Right? So it becomes lambda over n. And that's kind of what, if we had gone through probability theory, we would have got that same thing in this case, right? So our conclusion, right, what this theorem says is that lambda hat, based on n observations, is approximately normally distributed for lambda, and its variance is like lambda over n. And in larger samples, the MLEs are approximately normally distributed. Right? So our 95% confidence interval for lambda can be this, our lambda hat n plus or minus 1.96, which is the 95% ranges there. And then we put lambda over n, plug in our MLE for that one, and take the square root of all that. The square root of its sampling variance, sampling distribution variance, and you get a confidence interval. So that one works all the way through there. So we had n times the density multiplied together and did the logs and one derivative to find the MLE. To find the information, we go back to one observation, take a logs and two derivatives, and then the expectation. And then
we put our MLE estimator
in here, because if the parameter is still there, if it's still unknown, right, and we use that as kind of our estimated variance, right? So we get a confidence interval for it directly. Let's look at one more example. Which one? Is that a good one? Is this a good? That is what's fine. Right? So we did this one in the practice problems where xi is geometric with probability p. So the probability that xi is some value is 1 minus p to the xi minus 1 times p. So this is, in this version of it, xi is either 1, 2, 3, so on. Right? So how many observations do we have to have before we get our first? Right? This density, so here's the values of x, 1, 2, 3, 4, 5, etc. The first probability is at p. The probability, our first one is this success is p. The second one, the chance that our success happens on the second one, we have a failure and then a success. So 1 minus p times p. So it comes down, and the next one comes down and then keeps going down like this. Oops, this is at 1. Right? Above 1, 2, 3, and so on. So those are all the probabilities. We figured out that the MLE in this case is 1 over x bar. So you'll have a bunch of observations. How many times you have to wait? Right? You take the average number of weights, and our proportion is 1 over that. Right? This one's a little harder to deal with in probability theory because the mean and variance aren't of a 1 over x bar. It's not just 1 over the mean or 1 over the variance or anything like that. Because it's nonlinear, you'd have to do something else. You could do a bootstrap and get at the sampling distribution. That would be fine. Or we can also do this thing with information. Right? So with information, we start with one observation. So the probability that x equals some value in this case, 1 minus p to the x minus 1 times p. Let's take the log of it. x1 log 1 minus p plus the log of p. One thing that's encouraging is the x is now linear. So if we have to take expectations, that x is not in an exponent, not in a denominator or anything, it's there. So that'll make things easier eventually. Right? But we want to get at the curvature of the likelihood, so we take a derivative. So let me just call this, I'll just call this just an L. okay, instead of having to rewrite it all the time. The derivative of that L, I'll just call it L of P. It's not the likelihood, it's just one observation. So let's write one observation. Here, not today. I used a little script L of P for the log likelihood before, but this is just one observation. But I just don't want to rewrite that the whole time. So a derivative of this one,
Negative.
yeah, there's going to be a negative out front, x minus 1 over 1 minus p. The x minus 1 is like a multiplier. You get 1 over p there, but because of the chain rule, you get another negative. And this one plus just 1 over p. That's the first derivative. And we can take the second derivative. And so the x minus 1 is still going to be there. And this is 1 minus p squared. And then we get a negative negative. Because it's being in the denominator, it's like the negative 1 power. But by chain rule, we get another negative. So it's still negative. This one is negative 1 over p squared. A little more involved. Right? The expectation, right? Oh,
Didn't we already have a negative?
we did. There's a negative out here.
Doesn't that make 3?
It makes 3 negatives,
Which is a negative.
which is a negative again. Yeah. Then we want to take the negative of this whole thing and the expected value. The negative of the expectation of d squared L of p, dp squared. The negatives go away. The thing that is effective here is expectation works in a linear way. So what we ultimately have to do is just take the expectation of an x, and then this becomes plus. For the geometric, the expectation of p, x is 1 over p. So if we put 1 over p in there, and manipulate things to solve things out, the answer you get is 1 over p squared times 1 minus p. You do a process of putting everything over common denominators and factoring out terms. But this is the information then in one geometric observation about that parameter p. Right? Not a formula that automatically pops to mind, but this is what ends up getting to be over there. Right? So then the variance of p hat, remember p hat for the MLE was 1 over x bar, ends up is 1 over n times the information. So that's 1 over n, and then it was 1 over p
Squared 1 minus p.
Yeah. 1 minus p. So that's p squared times 1 minus p over n. And we get the variance. So whether you bootstrapped or did this calculation, you should get quite similar values. And so we would say a 95% confidence interval for p is going to be centered at p hat plus or minus a normal value. And then its variance, there's a p squared 1 minus p over n, and we use the standard deviation of that. And because we don't know p, we put in our best guess, which is the MLE. We're going to put little hats on these. And so we had a sample of values we could estimate, and we could get a large sample confidence interval for p, and that would tell us where the likely values are. So what's going on? Why does this work?
Yeah.
Huh?
Just
Just the math?
Yeah, no, that's dumb reason.
So we have, it's in this likelihood function, right? So let's say this is p hat, values p here. We'll make a graph. And then this is the log likelihood function. Where's our MLE?
Highest point.
Yeah, it's determined by the highest point. Right? The MLE is actually this one down here, the MLE on the p scale here. But this is where it's 0, right? So the derivative with respect to p of the log likelihood for p is z equal to 0, and that's what we find there. Right? So what are we doing with the information? Taking the second derivative, right? The second derivative of this log likelihood for the ones we deal with are less than 0, so they're concave, right? Which means that the slopes are changing from going more negative, so they're like this, right? And so this curvature up here, how fast that's going is related to this, right? And it's negative, right? So the negative of that, this is a square, got a square in there, of the log likelihood of p is greater than 0. And the likelihood tells us about where you think p is going to be, right? So if you had two likelihoods to compare,
That would be
and you had one likelihood that was like this, and the other likelihood, so here's p, and then the log likelihood function, and here's the log likelihood function. If this other one was, kind of like more spread out, right? The steeper ones
more erratic.
have more, well, it's changing faster, right? But where is p hat? Right? That one's very precise about it, right? You can't move the value very far without a big drop in the likelihood, right? So in some ways that likelihood determines it very closely. On this one, you could move p a fair distance and the likelihood value is kind of about the same, right? So this one is more precise information about p. And the curvature is more negative. So if you take the negative of that, it's more positive, and 1 over that is smaller, right? It's this whole chain of things, right? So if its curvature is steeply negative, it's really in there, right? It's very steeply negative. So the minus of that is very positive, and 1 over that is very small. Right? So more precise. So the d squared, dp squared of the log likelihood is a lot less than 0. This means there's kind of a lot less. And so then the d squared of that dp squared, when it's negative, is a lot bigger than 0. And then so 1 over that dp squared thing is small. Right?
A lot smaller than 0.
Yeah, well, it'll still be positive because if this thing's positive, so 1 over a positive, this can be very small. So a very sharp likelihood that says that you can't move away from that point without really depressing the likelihood value. Right? The steeper it is, the smaller the variance. Right? And in this case, it's less well determined. Right? You could move over here quite a bit, and it's a decrease, but not a very big magnitude. Right? So if it's not steep, you get the other type of statements, right? Then the log likelihood, the second derivative, is negative, but not that negative. So the negative of that is positive, but not so positive. And 1 over that number is not so small, right? So if you don't have a steep likelihood, you get big variance, right? And so this maximum likelihood theory with this information is picking up on that, right? So the interpretation takes a little while to think about maybe, but it's kind of that key role of the actual probability function, the actual likelihood in determining the estimator and how precise it's going to be. So it kind of does this naturally, right? You get more observations, generally the likelihoods get more peaked, get steeper, your variances get smaller, and it's reflected in that. So get this homework 5, which we'll be doing 1 week, just 1 or 2 problems to kind of go through this, but I'll kind of provide a few guides along the way, because it's certainly there's an expectation, so there'll be a little bit of help with the expectation, but a couple of these to go through to get up to the point of getting a confidence interval. And on Wednesday we'll do a couple more examples of it. So I think that's it was one of the major advances, I think, of the theory to come up with this and show that the maximum likelihood estimators are asymptotically normal. There's rigorous proofs of these things that would be based on real analysis or using things like and deal with these things. Can you differentiate functions once or twice? How smooth are they? And so on. And the world of probability theory then part of it deals with relaxations and modifications of that theory. But one thing that comes out of it is this large sample confidence intervals for maximum likelihood. So, okay, so we can go on break now. If you didn't think back to your exam, I have the exam and the schedule.
Yeah, that was gonna be my question. How the condition that it has a continuous second derivative. So like everything we're gonna be dealing with is gonna satisfy that?
Pretty much. Yeah. There could be some things where the state of nature kind of jumps from one space to the next. Only can exist in this. So there might be some things in quantum theory or some of these esoteric things that cause that problem. But
In general.
almost everything that we would deal with would be more smooth like that. There's a classic problem called mixture models, where you can jump from having one group to 2 groups or multiple groups. And so yeah, right. So you'd have, is it really 2 underlying populations mixed together or just a single one? And so that causes some complications, right? Because say for a normal, you'd have a mean and a variance in each group,
Yeah.
and this proportion. Well, if the proportion is 0, then you have a mean and a variance. And so you jump from 5 parameters down to 2.
Yeah.
Right? And so that jump, and measuring distance in that space, how close are you between so I don't know, we'll talk about hypothesis testing, right? So some of the hypothesis testing goes from, are you close to the null hypothesis or far away? But in that mixture problem, the space is irregular.
Yeah.
So you can't really kind of figure out.
Impose a metric.
Yeah. Yes.
I just wanted to ask about like the different symbols, because like looking for my exam as old, I think that's something I didn't do.
Mhm. Yeah, so these kind of the mu's, kind of the population means, the parameters, right?
And then the X bar is like the test statistic.
Yeah, like the sample average. So for the 36 that were in one group and 36 in the other group, those were the average values. So just distinguishing those there, right? Because we'll always do the inference about the parameters,
Mhm.
and then use some sample data to get a test statistic or something like that. So,
All right.
yeah.
Yeah, I was just thinking that I did that a lot of my homework without even realizing it, just kind of like interchanging it.
I mean, I can't recall so much of it. I think they were just like some numbers.
Yeah, and
Presented
you have a ton
and
of
so-
homework to look over too,
Yeah,
so it's that.
But anyway, so I can do a little better job of catching it on this, I suppose. But it's not a big penalty, because the sentiment and the general ideas
Yeah.
are correct, but kind of going forward, having that distinguishing those 2 things is good.
Yeah, I like getting the ideas down too, because I just I want to like make sure like I'm not using symbols just to use symbols, and I know what those symbols mean. So it's like yeah.
Are you going anywhere for break?
I'm staying here,
Yeah.
and trying to find people still who are staying here too. But I'm sure someone is.
Some people will be around, yeah.
Yeah, ghost campus.
Right. It'll be quiet, but it'll be nice to be calm for a while, so.
Yeah.
All right. See you.
Take care.